Hey everybody, Trey here. Welcome back to another video. Today we're going to talk about one of the more prolific early season tornado outbreaks in recent memory, and that is the March 2nd, 2012 outbreak from the Ohio Valley into the southeast that included several significant to violent tornadoes, most notably the Henryville, Indiana EF4 that you see on the screen here. This was a very widespread outbreak of severe weather, very favorable conditions over a large swath of the country. And we're going to focus on the Henryville storm in this video, but we're also going to touch on some of the other significant tornadoes that this outbreak produced, including the West Liberty and Salyersville, Kentucky killer tornadoes that occurred after the Henryville tornado. West Liberty tornado you see on the screen here, very menacing looking tornado. Very photogenic tornadoes in this outbreak, which is somewhat unusual for especially early on in the season. So we're going to take a look at why that might be the case. Usually, I like to give you guys a lot of journal articles, peer-reviewed research on these events. Unfortunately, this particular event does not have any peer-reviewed articles on the meteorology or tornado behavior of these tornadoes in this outbreak. So this video is mostly going to be a meteorological discussion. We're going to really do a deep dive into the meteorology behind this event. We will talk a little bit about some of the damage that these tornadoes produce, but again, this is mostly going to be a meteorological overview of this particular event. So let's go ahead and get started here. To put this outbreak in perspective, you can see from this storm report map a plethora of storm reports with this particular event, a very prolific severe weather outbreak, no doubt. Almost 1,000 severe weather reports across the entire region from the Ohio River Valley down into the southeast states, 160 tornado reports as well, and you can see that the favored corridor for tornadoes was mostly up in here along the Ohio River Valley. We'll talk about why that area was a little bit more favored for tornadic activity, especially significant tornadic activity, than areas farther south. Over 300 damaging wind reports and a bunch of hail reports. With the new research we've seen, given how the wind profile relates to the hail production in storms, hail-producing storms tend to favor weaker low-level shear environments. You often don't see such a significant tornado outbreak with so many hail reports, but you'll notice a plethora of hail reports, especially in areas to the north here, into Illinois and Indiana, as well as to the south. And you'll notice that we do have a little bit less tornado reports down here across the southeast states where we have some more hail reports. But we also have a plethora of hail reports mixed in with those tornado reports up there in the Ohio River Valley. So somewhat counterintuitive based on some of the new research we've been seeing as far as low-level shear and its relation to hail production. So we'll talk about that a little bit as well as we go into the meteorological discussion of this particular event. But nonetheless, an extremely potent, prolific severe weather outbreak by any stretch, every stretch of the imagination. This is the tornado track map centered on Kentucky. You'll notice we have a bunch of significant to violent tornadoes, especially up here along the Ohio River, just north of the Louisville area. This is the Henryville storm right in here. Also a few significant tornadoes out in that way as well. Notice to the south, not quite as many significant and long track tornadoes. Once again, we'll talk about why that might be the case in just a little bit. But we're also going to talk about some of the other significant killer tornadoes. The killer tornadoes in pink here, the non-fatal tornadoes in red. So numerous long track killer tornadoes up here in the northern portions of the outbreak. And we're going to talk about these as well, the West Liberty and Salyersville, Kentucky killer EF3 tornadoes that went along with the Henryville EF4. So the event started out as a high risk centered on the Ohio River down into through central Kentucky and northern Tennessee, surrounded by a large moderate risk area. 30% hatched area for significant tornadoes, surrounded by that 15 hatched area. So a widespread threat for strong to violent tornadoes with this particular event, as well as a significant damaging wind and hail threat. And again, you don't often see significant large hail fall within an area of significant tornado coverage, but we saw that at least to some degree with this particular event. We're going to talk about why here in a little bit. By the 1630 outlook, the high risk was expanded a little bit to the north into Indiana and Ohio. Same 30% hatched area within that high risk air sector, as well as the remaining damaging wind and significant hail threat. So a very potent event was forecast throughout the days leading up to and during the morning of the event. And this was certainly a well-forecast event by the Storm Prediction Center. All right, let's dive into the meteorology behind this event. We'll start out at 500 millibars like we always do, and you can see right off the bat a very sizable trough across much of the United States. The core of the trough centered up here in North Dakota, and the overall axis of the trough somewhat positively tilted at this point. This is at 12Z on March 2nd, 2012. Axis of the trough somewhat in that vicinity. And if we were to use our general rule of thumb that the wavelength, the length between the trough axis and the ridge axis, which would be somewhere in here, a little bit hard to tell, if it's the size of the United States or greater, the overall wave is not going to move that much. It may even retrograde back to the west. If it is smaller than the size of the United States, then it's going to move off toward the east. And you can see we have a pretty sizable wavelength here between the two axes. And so this trough is not going to be super progressive. It will move off toward the east a little bit with time, but it's not going to move very significantly off toward the east. So not an overly progressive system. The interesting feature here at 500 millibars as we go forward, notice right in here across Missouri, into Iowa. Little bit of a shortwave that develops within the main flow. And if you've been a supporter of the channel for a while, if you watch a lot of my videos, you'll know that these little low amplitude shortwave features embedded within the large scale flow really get my attention as far as severe weather goes. We've had significant severe weather events with very high amplitude, negatively tilted troughs, but oftentimes the forcing with those is quite strong. So you get a lot of storms to develop. Perhaps the overall deep layer shear vectors are oriented poorly with respect to the initiating boundary. So you get a very messy storm mode in some of these strongly negatively tilted, highly amplified features. With these little shortwaves embedded in the flow, the forcing is much weaker. The overall shear vector orientation with respect to the initiating boundary is often a lot more favorable for discrete storms. And so these little features, these little waves embedded in the flow really get my attention as far as severe weather goes. And that's exactly what we have here. You can even see it at 500 millibars. Usually we like to look at 700 millibars for those short waves. You can really see it here at 500 millibars across Missouri. This is at 17Z. Very low amplitude feature, very strong jet streak associated with this little shortwave. 100 plus knots of flow rounding the base of this little shortwave trough, moving into Illinois and Indiana. And you'll notice here, this is our favored region for severe weather in here, and we kind of get somewhat of a glancing blow as far as the overall trough goes. The main forcing, the main height falls associated with this shortwave trough. Again, that's the lowering of the heights in a particular location, the geopotential height being the height of the constant pressure surface, in this case the 500 millibar surface, above mean sea level. Those height falls generally initiate rising motion favorable for severe storms. And so those height falls are located a little bit off toward the north of our favored severe weather region. But we're still getting a glancing blow, especially with northern extent into the Ohio River Valley there in Kentucky with this particular shortwave trough. So very favorable look here at 500 millibars with this particular system. Very low amplitude shortwave, and you can even see that even better at 700 millibars. Very well defined shortwave within this broad wave across much of the United States. Very much better defined here even at 700 millibars. Little shortwave right in there. Takes on a little bit more of a negative tilt as we go into the afternoon hours on the 2nd. And this is pretty textbook look for a shortwave trough that will initiate severe weather. We're right in, not quite in the, well-defined exit region of this particular trough. We've talked about the exit region before. These troughs tend to have an exit region of the trough that is most favorable for, it has the most favorable ingredients, most favorable vorticity advection, etc. for severe weather. It's right in that exit region of the trough. And again, that exit region is a little bit off to the north, but we're still getting a little bit of forcing, and this overall strong 700 millibar wave, this shortwave trough, producing enough of an impact on this particular area, especially with northern extent. Again, that goes into why the northern portion of this risk area was a little bit more favorable for significant tornadic supercells. This shortwave, a little bit more of a glancing blow, a little bit more forcing here with northward extent to help get the storms to fire there and be a bit more severe in the northern portion of the outlook area. 850 millibars, very strong cyclogenesis here in the low levels, given that very strong trough aloft. You see that low-level jet closed cyclone here at 800 millibars. This is at 18Z on the 2nd. Very strong cyclone centered here across northern Illinois, with a very broad low-level jet to the south, extending off to the east and south of this particular low center. You can see 40 to 50, even 60 knots here up into from Mississippi and Alabama into Tennessee, Kentucky, into southern Indiana by 18Z, and that would continue to overspread the region as that 850 millibar cyclone moved off to the north. And you can see a little bit better low-level jet up in here, 50 to 60 knots up in here across Kentucky into Indiana and Ohio, whereas down here we can see a little bit of a decrease in the low-level jet, a little bit more veering or more southwesterly low-level jet than it is up in here. So the low-level shear to the south appears to be a little bit on the weaker side, even though still fairly decent for some strong supercells down there. A little bit stronger low-level shear up in here across the Ohio River Valley, hence maybe a little bit better environment for significant tornadic supercells up there. All right, let's go to our surface map here. So we'll start at 12Z and go through the morning and afternoon hours. So we'll start at 12Z. You can see a little bit of a semblance of a surface low somewhere in central to southwest Missouri. You can see those wind barbs switching around. Northerly wind barbs here in central Missouri, shifting to southerly and southeasterly across southern Missouri. So somewhat of a surface low there. We can actually see it a little bit better at 13Z. You start to see a much more well-defined surface low somewhere in here. Surface low moving off quickly toward the northeast as we went through the morning and afternoon hours here. Interesting surface pattern. I'm going to forward it a few hours. This is at 16Z, 17Z, and 18Z. So surface low looks to be somewhere up in this vicinity, up into south central Illinois. You can see those wind barbs switching from northwesterly here across western Illinois to more westerly across southern Illinois, switching to southwesterly or southerly across southern Illinois. So low center somewhere up in this vicinity with a cold front draped down to the south. A little bit tough to pick out here. You can see, we don't see a very strong wind shift associated with this particular boundary, but you can see a temperature and moisture drop off here. Dew points in the upper 50s with temperatures in the mid to upper 70s across southeast Missouri, southern Illinois, shifting to temperatures in the 40s and 50s out here across southern Missouri with dew points in the 30s and 40s as well. So the cold front looks to be somewhere out in this vicinity right in here. A little bit hard to tell, but again, we can tell by the temperature and dew point shift across that boundary. A little bit of a wind shift as well. Warm front draped across the region as well. This one also a little bit tough to pick out. You can see dew points there up into the 60s across Kentucky into southern Indiana. Temperatures do drop off as well. Temperatures in the 60s into central Indiana, 70s farther to the south. So the warm front is going to be somewhere kind of in this vicinity, I would put it. You see a little bit of a wind shift there in southern Illinois. We go through here, and it kind of drapes off somewhat like this, which is a little bit unusual. Usually we see that warm front draped out across the east, but it does kind of appear that it is going draped down a little bit farther to the south, which is going to have an impact on the eastward extent of the overall severe threat and the overall width of the warm sector going into the afternoon hours here across this region. So that low would continue off to the northeast through the afternoon hours, and by 20Z, right about the time of the Henryville supercells, you can see where that frontal zone is. The surface low is somewhere up into eastern Illinois, right in there, with a strong wind shift behind as the cold front starts to move in, as behind the discrete storms there, the winds at the surface start to shift out of the west a little bit. Still very backed winds here across southern Indiana into Kentucky, winds out of the south or just out of the south-southwest. And if we go back, we see a little bit better here. But notice that the winds across southern Indiana into Kentucky are a little bit more backed, and look farther south across Tennessee into Alabama. The winds are at the surface are much more out of the southwest, much more veered down here. So given that we had a little bit more veered low-level jet and veered surface winds to the south, the low-level shear and the overall wind profile is not quite as favorable for significant tornadoes farther south. Still likely had some very strong low-level shear down there, and deep layer shear as well for supercells, but the overall low-level shear was not nearly as favorable as it was up here, given a much more backed low-level jet and backed surface wind up here across the Ohio River Valley into eastern Kentucky. So that was definitely a contributing factor to why the northern portion of the outlook, that high-risk area, was centered up into the Ohio River Valley, southern Indiana, southern Ohio, into Kentucky. A little bit better, much better low-level shear up here. And that also goes to the hail threat with southern extent especially, into Mississippi and Alabama and Tennessee. A little bit less low-level shear, made for a little bit greater threat for significant hail in those regions down there as opposed to up here. Still had some hail reports up here as well, especially early on. Some of the storms were initially elevated. We'll talk about that in a second, but we still had a favorable environment for some hail up here initially with these storms. Moving on into the afternoon hours, when we started to see additional storms here into Kentucky, you see those winds at the surface stay fairly backed, especially into eastern Kentucky where those supercells began to fire. Notice the winds here across the region now much more out of the west behind the cold front at this point. If we were to place the cold front, it probably would be somewhere in this vicinity here. You can see the wind shift. So the cold front definitely catching up to the storms here. A little bit tough to tell, but definitely pinching off that warm sector as the surface low moves off toward the northeast. That warm sector kind of pinching off with northern extent as we went into the evening hours with this particular event. Taking a look at our visible satellite imagery, this is at 8:45 a.m. on March 2nd. You can see that storms have already started to fire across Missouri into Illinois, widespread storm development up there. Those will be initially elevated north of that advancing warm front as that low moved off toward the east and started to continue to pull that moisture northward. These storms were well north of that warm front boundary. But ample clearing out here in the open warm sector, so we started to get surface heating from early on in the morning, and that was a favorable sign to build some instability in this particular environment. A lot of times these early season cases lack on the instability side of things. Strong deep layer shear and low level shear often, but the instability is lacking. Not quite in this case. We had that very strong trough moving in, weakly capped warm sector, and a surface heating environment that was favorable to build some instability. And we go on into the morning and afternoon hours. Just a very favorable look there both along the cold front. As storms fired, you can see the cold front boundary, the western edge of that cumulus field, with several supercells developing out in this cumulus field in the open warm sector. As we moved into the afternoon hours by about midday, widespread storm development along the cold front and ahead of that cold front as it moved off toward the east continued. Cumulus field down here into Tennessee and Kentucky, where additional storms would fire as we went into the afternoon and early evening hours. So overall, a very, very favorable look on visible satellite there. Let's move to our radar imagery, and we'll start going through a progression of this event. So storms fired quite early across far southeast Kansas into southwest Missouri. Those were our first storms that developed there in this particular regime. These would initially be hail producers, and we'll take a look at a sounding here as they moved off into Missouri and Illinois. You can see some stronger cores in those storms. Here is a sounding from St. Louis at 12Z, and this is a pretty good looking hail sounding. Some elevated instability here. You can see some elevated instability in place above a strong capping inversion there at the surface. Once again, this was removed from the warm sector, so dew points only in the 40s, temperatures very low in the low 50s, so that instability was somewhat elevated. A little bit strong low-level shear, but again, because this instability was elevated, we're not using this lower portion of the sounding. The instability starts here at just above about 2 kilometers or so somewhere right in here. And as you can see, if we just look at this portion of the hodograph, very favorable look for a hail situation. Strong deep layer shear for some rotating updrafts and stronger updrafts with very limited low-level shear with respect to the base of the storm and base of the inflow air that is feeding that storm. So very favorable look for large hail early on with these storms. Multiple storms also fired north of that advancing warm front in the warm sector. Once again, those were elevated as well. So we had a number of large hail reports early on with those storms. But by about 14Z or so, 14 to 15Z, we started to see surface-based storm development here back in southeast and central Missouri near the cold front. And we'd also get additional development out ahead across southeast Missouri into Illinois that would eventually become our significant tornado producers as they moved into the Ohio Valley region. Just a quick look at the 12Z observed Little Rock, Arkansas sounding. You'll notice a couple of things here that we're in the warm sector, just east of that advancing cold front. In the open warm sector, dew points in the low to mid 60s, which is strong, at least decently strong for this time of year. But we're already fairly uncapped, almost fully uncapped here, and this is at 12Z, so 6 a.m., almost fully uncapped. So we would expect the event and storms to actually initiate as that trough moved in fairly early on, given an uncapped or weakly capped warm sector. Already some strong instability building in, almost 2,000 joules per kilogram of mixed layer CAPE, and a very favorable looking wind profile for supercells. Strong deep layer shear, 0 to 6 kilometer shear, approaching 70 knots with effective storm relative helicity of 300 knots. So strong low level and deep layer shear, favorable for tornadic supercells in a very weakly to almost fully uncapped warm sector with strong instability. This early environment would only improve with time and was a harbinger of the significant tornado outbreak that was about to get underway in just a few hours. All right, let's take a zoomed in look at the radar. We'll start at about 1430Z as storms are about to fire. And as we said, given the somewhat weaker forcing aloft from the lower amplitude trough feature at 500 millibars, the non-progressive upper air and surface pattern, and the overall weakly capped warm sector, we were expecting a fairly favorable environment for discrete supercells. Even if we look along the cold front, if we take a look back at our surface map, we'll go to about 15Z, and so our cold front is somewhere oriented like this, surface low up in here, and our cold front oriented somewhere in this vicinity. So a somewhat northeast to southwest oriented boundary. So keep that in mind, and we'll take a look at our bulk shear vectors, or 0 to 6 kilometer shear vectors, to look at our initiating boundary with respect, or our shear vectors with respect to the initiating boundary. So something that looks like this. Our shear vectors are decently perpendicular, have a decently perpendicular component with respect to the initiating boundary. So even along the cold front, discrete to semi-discrete supercells were a likelihood, at least early on in the life cycle of this event. So we'll start off here again at 1430Z, and we'll zoom in here to southeast Missouri, southern Illinois, southern Indiana, into Kentucky and Tennessee. So we go on here, and you see just widely scattered storm development both along the cold front, some more discrete elements in there. You see this is closer to our cold front, some more discrete elements in there, with some open warm sector development. As we said, the weakly capped warm sector was favorable for some discrete storms along it, or in the warm sector, as we started to initiate storms. Again, along the cold front, not some definitely more discrete storms there, given a fairly favorable shear vector orientation with respect to the initiating boundary, with northward extent closer to that surface low. And these warm sector storms would eventually evolve into the tornado producers here. So we had these storms. This would be a robust supercell early on. We were also watching this cluster of showers fire up out ahead. That would eventually become the Henryville tornadic supercell. So let's switch radars here, get a little bit of a more eastward view. So this is from the Louisville radar. Here's our robust supercell ongoing. Here's our new development out well ahead of everything in the open warm sector. So watch what happens with those storms. We get 3 robust cores there, 3 robust storms to fire up. And watch what happens here with the southern one and that middle one. We undergo a storm merger, and we've talked about storm mergers before. You can have constructive or destructive interference. You can have a destructive interference when 2 storms merge with each other and they eventually just fizzle out, not doing much. We can also have constructive interference, and we've talked about this with a bunch of different past events. For example, El Reno. A couple of the events from last year, particularly November 4th, the Sulphur Springs tornado from November 4th, 2022. That storm underwent a merger before producing that tornado. Same thing happens here. We get a favorable storm merger, and we get a single supercell to emerge ahead of the already robust supercell behind it, and this would become the Henryville tornado producer. Would quickly become tornadic once that merger happened, and you can see just a classic look there on radar. If we zoom in a little bit, we'll take a look at the radar. So that's the white circle there. This is from the NWS Louisville office in their event breakdown. I'll link to their event page in the description below. But that lead supercell is in the Henryville supercell is in the white circle. And just a classic, absolutely classic image there with some semblance of a debris ball there within the hook, and that precipitation being fanned out well ahead of it. Again, these were very visible tornadoes, and we're going to do a little bit of a hodograph breakdown and discuss why that was the case, but very visible tornadoes here. There's our trailing supercell, EF4, the lead supercell producing the EF4 as it moves through Henryville, right about there, and continues to produce tornadoes as it moves off toward the northeast. The trailing supercell also produced a tornado on the heels of the initial tornado that went through Henryville, was an EF1 that produced damage in very close to some of the same areas that received damage from the initial tornado. Here is the velocity of these storms. Very strong couplet you can see there. Again, this is aliased data. Usually if you're looking at radar scope or any radar product on your iPhone, you'll see that de-aliased data means that the radar has been folded. This, as we know, greens are inbound velocities going toward the radar, reds going away from the radar. But because this is being aliased, the winds are so strong in this portion, in this sector of the radar imagery, they have folded over to the other side of the image. We talked about that in the previous video on a previous case study on the Iowa derecho from 2020. I'll link that in the description as well, so you can go back and look at my discussion of range folding and velocity aliasing in that video. But so these are not actually inbound velocities. These are just very, very strong winds, strong outbound pixels that have been folded over. So very strong winds associated with this tornadic couplet, which is right in there going through Henryville, producing EF4 damage. And you'll notice that the trailing supercell also produces a pretty strong couplet there and does some EF1 damage with that as well. So let's look at some soundings here in proximity to this storm. We'll start off with an observed sounding. Let's go to 18Z at Nashville. So 18Z, Nashville, Tennessee. Let me zoom in a little bit here. So again, 18Z, midday at Nashville, Tennessee. Fully uncapped air mass here. About 1,300 joules per kilogram of mixed layer CAPE. Little bit of an inversion left. We've seen that before. Sometimes this doesn't make a difference. Sometimes just a couple degrees make a difference. We saw this on the May 20th, 2019 event, that this very similar look to the, with a little bit of an inversion there, about 700 millibars in the atmosphere. Not the case with this event, especially with northern extent closer to that shortwave trough, closer to the surface low. This little inversion that remained was not really an issue and was not evident on the soundings that we'll see here in a second. But very strong looking wind profile for significant supercells, very strong deep layer shear, 0 to 6 kilometer shear above 60 knots there, with effective storm relative helicity. Even though we have somewhat veered low-level winds, we still had quite a bit of low-level shear to deal with, over 250 meters squared per second squared of effective storm relative helicity. So a very favorable environment for tornadic supercells here with all hazards. Now let's take a look at some RUC model soundings. The RUC, again, is was replaced by what we know now as the RAP model, the rapid refresh model. But back then, in 2012, we had the RUC model, and it basically does the same thing. We can pull some soundings in proximity to our tornadic supercell here and go through a little bit of an analysis. Just for some context, this is from Louisville, Kentucky, which is just south of Henryville. Henryville is right here, Louisville right in here. So our soundings are going to come from right here, just a few miles to the south of our tornadic supercells moving through Henryville. So we'll start at 12Z at Louisville. Once again, north of the retreating warm front, some decent elevated instability, most unstable CAPE, about 1,800 joules per kilogram. So we were already destabilizing the atmosphere, although it was well elevated above that near-surface stable layer. And as we went through the day, that near-surface stable layer would erode quite efficiently. And by 18Z, we were fully destabilized, albeit still somewhat weak, low-level instability there, but dew points had surged into the low 60s, temperatures in the upper 60s there, with a very favorable-looking hodograph for significant tornadic supercells. Very strong curvature there in the low levels, with deep layer shear over 70 knots. So we go on the next couple of hours, 19Z and 20Z. Little bit of convective contamination here in this particular sounding, but doesn't have too much of an impact on the overall environment. But if you look at that, 72 over 60 at the surface, that means LCLs are not super low. Often in these events, we get temperatures maybe in the 60s, in the mid to upper 60s, with dew points in the the low to mid 60s. So your temperature dew point spread, and therefore your lifted condensation level, your effective cloud base, so to speak, are fairly low, and you get somewhat grungy tornadoes often with these types of events. Not really the case here. The lifted condensation level, the mixed layer lifted condensation level, above 1,000 feet in the atmosphere. So that means that we had cloud bases a little bit higher than normal, and that means our tornado is going to be a little bit more visible. Now we'll go into a little bit more of a hodograph discussion here in a second. You can see already this is a very favorable looking hodograph for significant tornadic supercells. Effective storm relative helicity over 600 meters squared per second squared. Again, a little bit of convective contamination here, but still very impressive storm relative helicity, very strong streamwise vorticity. Again, streamwise vorticity, we've talked about this in previous videos. That is when we take our storm relative wind vector from our storm motion back to our point of interest on the hodograph, and we take our horizontal vorticity vector, which is perpendicular and to the left of the hodograph. And when those two vectors are parallel, you have purely streamwise vorticity. And you can see in the low levels here that we have very ample, very much streamwise vorticity there, especially in the near surface layer. So ample streamwise vorticity, you can think about it as an NFL quarterback throwing a football with that perfect spiral. Those storms, these storms in this environment are ingesting that perfectly, purely streamwise vorticity, and that is much easier to tilt into the vertical and make a tornado out of it than crosswise vorticity, which is when these two would be perpendicular to each other. So very favorable environment for significant tornadic supercells here. Very strong instability as well, approaching about 2,000 joules per kilogram of mixed layer CAPE, so very unstable environment, unseasonably unstable environment. With this amount of wind shear, especially low-level shear and streamwise vorticity, no wonder significant to violent tornadoes were in the cards for this particular event. So I'm going to go back a couple of hours to our 18Z Ruck sounding from Louisville, and we'll focus in on the hodograph. And what we can do using the wind profile and the hodograph is take a look at a few different things that can tell us the type of supercell we're likely to see, such as classic high precipitation, low precipitation, the size of the supercell, how visible any tornadoes from those supercells might be, etc. And the first thing we can do, and we've done this in videos past, is compare the presentation of the storm on radar to our wind profile using the hodograph. So I'm going to go back to our radar imagery of the Henryville supercell, and I'll do a little double box here. So we have our supercell on the left and our hodograph from our 18Z Ruck Louisville sounding on the right. So you'll notice on the radar imagery, we have a tornado ongoing, mesocyclone region right in there, precipitation vented off nicely to the northeast. And if we compare that to our hodograph, we kind of get that sense as well. Our mesocyclone region down in here, and our precipitation is being vented off away from the mesocyclone region, and we get this little bit of backing in the mid-levels. And what that does is it helps to vent the precipitation away from the tornadoes and the mesocyclone region in the supercell. And that translates very well to our picture over here on the left of the supercell. Our mesocyclone region here, if we were to transpose this hodograph on top of the supercell, and I'm just going to do a rough drawing here, it would look something like that. And you can see it follows the storm fairly well. Mesocyclone region / tornado region right in here, and our precipitation is vented well off away from that mesocyclone region thanks to a little bit of backing in the mid-levels, and thus that precipitation is shunted northeast away from our region of interest in the storm. So we've done that before in some videos past, and that is a nice rough way to figure out how the wind profile might affect the orientation of the storm, or the construction of the storm on radar, and how well the precipitation is vented away from any tornadoes that might be ongoing with these supercells. And we said that these tornadoes were very visible. That was partly the reason. Next thing we can do is look at storm relative inflow in our 0 to 1 kilometer region. So storm relative inflow is just going to be our vector from the storm motion to our hodograph, generally in the 0 to 1 kilometer region for this particular exercise. So that'd be something right in here. Our storm storm relative wind vector going to our 0 to 1 kilometer layer on the hodograph. And the reason that is important is because it tells us the size of our storms. The longer this vector is, or in other words, the greater the storm relative inflow, the larger the supercell is going to be. If you have a storm relative wind generally less than about 25 knots or so, you have what's called mini supercells. You'll have little small supercells, very compact updrafts, that are not very sizable at all. If you have storm relative inflow above about 35 knots, you'll have much larger supercells. And so you can see that this particular vector here, if we were to once again draw that vector in, let's say it starts about here, we have 10, 20, 30, 40 knots, about 40 to 45 knots of storm relative inflow. That is very, very large storm relative inflow. And you can see on the radar picture here that these storms were not small by any means. I'm going to put both supercells on here. These storms were not small by any stretch of the imagination. Usually in these low cape, high shear events, you'll often have storm relative inflow that is weak, and generally storms that just look like kidney beans on radar. We see this in the southeast very, very often in these cool season events. You'll just have these kidney bean type shaped supercells, and that is usually these mini supercells. That is because the storm relative inflow is usually very weak. Not the case here. Our supercells much larger than is typical for these types of events, and therefore we have a fairly wide area within the storm's path that is producing severe weather, large hail, strong reflectivity cores producing large hail, as well as tornadoes with these particular supercells. We can also look at the storm relative outflow, especially in the mid and upper levels of the wind profile. And the storm relative outflow is simply the same thing. We're looking generally above 6 kilometers, and that would be this portion of the photograph in general, that yellow portion there. And the storm relative outflow is simply, we're drawing a vector from the storm motion vector, storm motion to our photograph here above 6 kilometers. And the larger that vector is, the larger the storm relative outflow, the greater the chance for precipitation to be vented away from the region of interest, i.e. the region of mesocyclone or tornado in a particular supercell. And that goes along with what we did at first with comparing the shape of the supercell on radar to our wind profile. Very similar here. The strength of the storm relative outflow tells us how visible, or generally the supercell type that we might see with a particular event. The rule of thumb is storm relative outflow in a deep layer above 6 kilometers greater than 40 knots is favorable for more low precipitation supercells, while much weaker storm relative outflow, generally below 20 knots or so, tends to give you more high precipitation supercells. So if we look at the length of this vector, we have 1, 2, 3, so just about 30 to 35 knots of storm relative outflow above about 6 kilometers. So that's right in that sweet spot for classic supercells. As we said, below about 20 is more so for HP supercells, low precipitation above 40. We're encroaching on that range for low precipitation supercells with about 35 knots or so of storm relative outflow above 6 kilometers. We're looking right in that range for classic supercells. Enough storm relative outflow where that precipitation will be effectively vented away from the low-level mesocyclone region, and thus we see very visible tornadoes in this case. If you're looking for more information on these hodograph techniques, I highly suggest going to Cameron Nixon's blog article on the storm relative hodograph. It goes through all of this stuff we just talked about in a really concise and informative fashion. So I'll put the link for this in the description below, but definitely check that out if you are interested in learning more and going deeper into these hodograph techniques. The Henryville tornado first initiated on the south side of Fredericksburg near Palmyra, moved off toward the northeast near New Pekin, and then took a path directly into Henryville. This is what it looked like initially near Palmyra. First took on a multi-vortex characteristic. You can see the different little vortices there with this particular initial stages of the Henryville tornado, and then eventually consolidated into one stronger vortex that you see here. From this pretty impressive footage here of the early portion of the life cycle, you can see some very intense motion within this initial tornado. Even early on in its life cycle, you'll see some power flashes here as it does some damage early on in its life cycle, moving very, very quickly, very rapid motion within that tornado, and it actually produced some pretty impressive damage early on in its life cycle. This is a photo from Simon Brewer near Palmyra, Indiana, showing that the tornado took 6-inch thick chunks of asphalt and ripped them up and tossed them across the roadway. That takes a pretty strong tornado to do that kind of damage. So very impressive tornado early on in its life cycle in its multi-vortex stage. Obviously, we've seen studies before that show that those multiple vortices can produce some pretty insane wind measurements. Some studies have shown up to 700 miles per hour. So very strong multi-vortex tornado early on in its life cycle, then consolidated into a large tornado. We recall from our initial video that we showed, this is from Skip Talbot, just incredible footage here of the tornado as it morphed into a wedge and then a very stout stovepipe-shaped tornado as it approached Henryville. Takes on some pretty interesting characteristics as it moves into Henryville. We've seen this kind of thing before. Notice that exterior satellite vortex there that we've seen with many other violent tornadoes, including the Tuscaloosa tornado. Here's an image from the ABC 3340 live coverage there. That tentacle orbiting around the main tornado. That is common in violent tornadoes, and Henryville definitely fits the bill as far as violent tornadoes go. This is some photo of the damage in Henryville. Pretty impressive damage there. Some homes completely flattened. Some pretty heavy damage to some industrial buildings. So a very strong tornado, no question. And it carved a 49-mile path through Indiana and some far northern portions of Kentucky. The supercell would eventually move on. Let me go back to the radar here. The supercell, so this lead supercell, as we remember, was the Henryville storm. This would be our most long-track cyclic tornadic supercell of the day. You can see it continues on and would produce multiple strong tornadoes as it moved off into portions of Kentucky. If we go back to our map here of the tornado tracks, you can see that this was definitely the most cyclic tornadic supercell of the day. Produces the EF4 Henryville long tracker, the short-lived EF1 that took nearly the same path as the initial Henryville EF4, would go on into Kentucky, cycle, and then produce another EF4 that hit the town of Crittenden, Kentucky, and then quickly after that produced a killer EF3 that moved near Moscow, Ohio. Here is a damage photo from Crittenden, Kentucky. You can see that this house was swept away pretty completely there, so some impressive damage from those tornadoes. Unfortunately, all of the tornadoes spawned, all of the strong to violent tornadoes spawned by this, the Henryville supercell, were killer tornadoes, as you can see from the map here. As the Henryville storm was ongoing, we had continued discrete storm development out ahead in the open warm sector. This is at 21Z, so 3 p.m. on March 2nd. And keep an eye on those storms out there. You can see that they really start to ramp up pretty quickly, and this would become the West Liberty tornadic supercell. There takes on a just textbook shape as it moves into eastern Kentucky. Notice that along the cold front, we still see quite a bit of cellular development, not quite a solid line of storms just because of that somewhat favorable orientation of the 0 to 6 kilometer shear vectors with respect to the initiating boundary. But our most tornadic supercells were going to still come from the discrete storms out ahead of that broken line of storms. And again, this was the West Liberty, the storm that would produce the West Liberty, Kentucky storm, or tornado. And then we had continued discrete storms out just ahead of the line. That storm right there would become the Salyersville, Kentucky tornadic supercell. Absolutely textbook storms on radar. This is the close-up of the West Liberty storm. If you were to look up supercell, a picture, radar image of a supercell in a textbook, you'd probably see something like this. Absolutely textbook look there. Strong reflectivity core, likely producing some semblance of large hail with a debris ball at the end of the hook. Just an absolutely classic look there from the West Liberty supercell. Then went right through town. We saw some footage of that earlier from this particular vantage point. This is another view of the West Liberty storm. Pretty textbook as well. Once again, those LCLs, or heights of the cloud base, a little bit higher than normal, so these features were much more visible than usual, also due to the venting of the precipitation off away from the mesocyclone region. But here's your wall cloud. Classic inflow tail feeding into the storm, and just an absolutely textbook look both on radar and visually from this particular storm. Here is a close-up of the tornado as it moved into West Liberty. Not a very large tornado, very large wall cloud, but you can see the dirt and debris being kicked up there underneath the mesocyclone. So a damaging tornado nonetheless. The Salyersville storm took on a very similar look. This was the West Liberty storm up here after it moved into West Virginia and your southern storm there near Campton initially is your west or your Salyersville storm. Once again, an absolutely textbook look. Just look at that, how wrapped up that hook is. Just absolutely textbook there. Debris ball at the tip of the hook moved right through Salyersville, producing some significant damage. Here are some damage pictures. This is from West Liberty, some pretty significant damage there. And here is from Salyersville, some homes completely flattened there. So now let's take a look at, let's do a quick sounding analysis. Again, we'll use the RUC model. This is from Jackson, Kentucky, to give you some perspective of where that is. Jackson, Kentucky is the red dot down here. Oops, you can't really see it. Here is Jackson, right in here. We'll zoom back out for you. So Louisville is over in here, Jackson is here, and West Liberty and Salyersville are just to the north and northeast of Jackson. So pretty good proximity sounding here. So we'll go start at 14Z going through 0Z, about the time that the tornadoes were ongoing in the West Liberty and Salyersville supercells. We start out here at 14Z, once again, very strong surface inversion north of that retreating, north or east of the retreating warm front. If you recall, the shape of the warm front, especially with southern extent, dipped a little bit to the south. You can actually see it if we pull up the surface map here. We go forward. Your warm front actually is draped somewhat out this way, and your cold front back in here. So the eastern edge of that warm front was the eastern extent of the warm sector, and therefore the overall significant tornado threat. So we were out of the warm sector. We gradually get into the warm sector as we go through the afternoon into the early evening. Moisture, not quite as favorable down to the south, is still well within the bounds for tornadic supercells within this particular environment, but a little bit less moisture farther south than there was up near the surface low, where we saw low to mid 60s dew points. But look at that photograph. Deep layer shear very strong, once again over 70 knots of deep effective bulk shear, over 400 meters squared per second squared of effective storm relative velocity. So given that you had a discrete storm mode, any supercell, any right-moving supercell, which we're actually firing in this particular environment, we're going to take great advantage of this deep layer and low-level shear combination to produce significant tornadoes. Now look what happens as we go into the early evening hours. The hodograph just goes absolutely bonkers. This is at 0Z. I mean, this is just nuts. Maybe a little bit better representation here at 23Z. Look at the veering and the strengthening of the winds as you go up into the atmosphere. That hodograph, the 1 kilometer point is about right in here. So extreme low-level shear. 0 to 1 kilometer storm relative velocity of almost 800 meters squared per second squared, with 0 to 3 SRH over 1,000 meters squared per second squared. That is just absolutely nuts, with some instability to speak of. So no doubt, no question why these were producing significant tornadoes as far as the wind profile goes. Now, the interesting thing is the instability profile. Notice that the capping inversion starts building in, and we never really fully erode the cap out here, maybe about 21Z, but it starts to build back in, and we start to get toward the eastern bounds of the actual warm sector. So let me go back to the wide view of the radar here just to give you a general position of where these storms were. This is your West Liberty storm. This was your Salyersville storm. Here is the Jackson radar right there. So they move off into eastern Kentucky, producing significant tornadoes, then into West Virginia, continuing to produce significant tornadoes. But the interesting thing is that cap builds in and we start to run out of warm sector. Let's take a look at our mixed layer CAPE plot here. So this is eastern Kentucky. This is our area of interest. Watch the eastern bounds. The eastern bound of the warm sector is going to be where these the red lines end. So right in here is going to be your eastern edge of the warm sector. Notice how those storms fire very much on the edge of that warm sector and then start to travel away and out of the warm sector into much more stable air. Yet they continue to produce significant tornadoes. We talked about this a little bit in the Greensburg case, where you can have very strong low-level and deep layer shear that will initiate some physical and dynamic processes, some pressure perturbations that can actually drill through the stable layer that starts to develop nocturnally near the surface. Now, the difference between the Greensburg, Kansas case and this case was that you had storms that were maturing while that convective inhibition or surface inversion was building back in. In this case, you had storms already mature within the warm sector and producing significant tornadoes. By the time they moved out of the warm sector, they continue to produce significant tornadoes. And Rich Thompson from the SPC actually talked about this in his tornado forecasting workshop, that if you have mature supercells ongoing, we'll pull up the reflectivity here, if you have mature supercells ongoing and they move into a much more much harsher environment as far as low-level instability goes, or deep layer instability goes, they can actually persist for quite a while. These storms are going to try all they can to not dissipate. Eventually, the unfavorable environment will get to them, but if they are in a somewhat steady state, producing significant tornadoes, and they run out of real estate, so to speak, as far as the warm sector goes, they're going to still be strong and produce tornadoes well after they run out of warm sector, because they're such strong entities and they're such steady state entities. So that was one reason that these continue to produce significant tornadoes well after they ran out of real estate. You notice the tornado tracks here, significant damage well into West Virginia, even though that was never really within the warm sector. If we look at our SPC map, mixed layer Cape map, this is at 0Z. Notice that the West Liberty storm already well into West Virginia at this point, still producing significant tornadoes. So very interesting that these ran out of the warm sector, ran out of the favorable instability, and had some convective inhibition building in there at the surface, but still continued to produce significant tornadoes. It's because these things are beastly storms, and they start to become steady state, and they're cyclic tornado producers, and a combination of strong low-level shear continues those pressure perturbations within the storm and allows those storms to continue into an unfavorable instability parameter space for tornadoes quite a ways, and that's exactly what we saw in the Salyersville and West Liberty storms. So that's going to wrap things up for this case study. Hopefully you learned a thing or two from this event. This was a pretty interesting event meteorologically, especially early in the season. Very potent event for this early in the season. Unseasonably strong instability and wind shear came together to produce an outbreak of significant to violent tornadoes across the Ohio River Valley into the southeast. Very interesting, and one of the more prolific early season outbreaks we've seen in quite a while. With this active pattern we're having right now, one only can wonder if one of these outbreaks is on tap as we go into the next few weeks, toward the end of February into early March across the U.S. So with that, thanks for watching, and we'll see you in the next video.